So today you are going to do a synthesis of benzene. So with benzoin, our starting material, and you also are going to use ammonium nitrate, okay, and copper acetate.
So you're making benzil, B-E-N-Z-I-L.
Yeah.
And from what's the starting material?
Benzoin.
Benzoin.
Yeah.
Benzoin.
Yeah.
Okay, we'll draw it later.
Yeah, we're going to do it on the board.
We'll draw it on the board later.
Yeah.
Okay.
So what do we need? So we need a jack, which you see here.
You need a jack.
Jack. We need a sandbar,
And a sandbar.
which you see here. We need the boiling chips.
Boiling chips, they
Yeah.
used them before, yeah.
Yeah. We need cupric acetate.
Cupric
Acetate.
acetate. Is cupric two things? Like
Yeah, it's
copper,
oxidation number 2, yeah.
copper to acetate.
Acetate, yeah.
Got it.
So you need ammonium nitrate.
Ammonium nitrate, yep.
Yeah. We need benzoin, that's the starting material. Benzoin.
Benzoin,
Yeah.
okay.
We need Büchner funnel.
Büchner funnel, yeah,
Yeah.
for vacuum filtration.
Yeah. We need a condenser.
Nice big condenser, okay.
Yeah. We need a 50 milliliter round bottom flask.
Round bottom, okay, for the reaction, I guess.
Yeah. We need a plastic funnel, as you see here.
Big plastic funnel, yeah.
Yeah. We need a hose.
And a hose.
Yeah. We need 50 milliliter LMR flask. That will be for purification later.
This is later for the purification
Crystallization,
flask, yeah.
Yeah. So the first thing we do, we have here the round bottom flask.
Yep.
And clamp the round bottom flask.
Clamp it up, alright.
So now, with that, now
Yep.
we need to fill that. Now we first fill that with a boiling stone.
Boiling stone
The
inside.
boiling stone is basically the boiling chips.
Boiling chip.
Yeah.
Is it in there?
Yeah,
Let's see it.
you see that here?
I see it.
Yeah, it's one here. I can add a second one.
Why not?
It doesn't hurt. See that here?
Alright. A couple of them. Alright, cool.
So now you are going to add first 0.4 gram of ammonium nitrate.
0.4 grams.
Yeah, 400 milligram.
400 milligrams of ammonium nitrate.
This one is not a good stuff, as you know.
Yeah.
So
Isn't
people
it
can do nasty things with that.
explosive, right?
Yeah, yeah.
I think under the right circumstances it's explosive.
It is, yeah.
But this is maybe a little bit of wet, a little bit of water, so it makes it less explosive.
0.4.
0.4 or 400 megs.
Yeah.
Looks like a nice little white solid.
Mm-hmm. Well, yeah.
Yeah. Looks like sugar.
It looks like, but it's not.
I wouldn't put it on your
No.
in your coffee.
No,
Probably pretty toxic too.
it is.
Yeah. Oops.
Yeah,
Do you overdo it?
yeah, that was too much.
Alright, they're almost there. 420 megs and
No, I just need a little because it's...
you're at about 390 megs. There you go.
No, oh,
Let's
okay.
see, where are we? Ah, 400 megs. What does it look like?
Yeah, 400 milliliters.
Okay.
That's what
Yeah,
I'm
basically a white solid. Okay, cool.
Yes, I need to close that.
Cap it up.
Yeah. Cut it. Let's put that here. Then we will need 1.5 grams of benzoin.
1 point how much?
1.06 grams.
1.06
Yeah.
grams.
Yeah.
So, yeah, 1.06. The gram plus about 60 megs on top. And this is the benzoin or
That's benzoin.
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 Benzoin. There it is. All right, 1.06 grams.
Yeah.
Almost there.
Just a
1.02.
little.
1.03. 0.04. 0.05. There it is. So this one also looks like a kind of like a sugary white white solid.
Yeah.
Okay, cool. A lot of organic molecules do.
Yeah.
So you're just going to mix them all up,
Yeah.
put them into the funnel.
Put them to a round bottom flat.
That's pretty easy.
Yeah.
Dump them in.
So
Okay.
now you need 20 milliliters of benzil.
Cupric acid.
Yeah.
Or copper acetate.
20 milliliters of cupric acetate.
Cupric acetate, that's
Yeah.
right, yeah.
Of that. Use a beaker.
Okay.
It's exactly 20.
20 mils.
Close that.
Kind of blue because of the copper, right?
Yeah. Acetate.
It's probably also a little toxic. I think all the copper salts are sort of toxic.
Yeah.
Looks like Kool-Aid or some kind of.
Yeah. So now.
Okay, condenser.
Setting has to be well done here. It is.
Yep.
Hot plate. And bring that up. Bring that down.
Is the sand bath hot yet, or are you?
No, not yet.
Right now it's room temperature.
Yeah.
Okay. I normally just stick my hand in it.
Yeah. There is no problem with that right now because it's not hot.
Yeah.
Last time that was too hot.
You preheated it.
Yeah.
Okay.
So we have that here, and it's set to go until 5.
I think you're backwards. I think this goes
one
there.
Yeah, that's over here. Yeah. And this one goes over here.
Okay.
So you need to go until I want.
So we have let's make sure we understand this.
Yeah.
We have the sand bath going into the regulator, and the regulator goes into the power.
Yeah.
And what's your setting roughly?
I'll put that at 6.
About 6. Okay. And do you want it to boil, or?
Yeah.
Okay, so we want to boil it up.
25 minutes.
For about 25 minutes. Okay, cool.
Yeah, about.
And the sand, maybe we should put a little bit of kind of a. I like to dig. A nice contact. Yeah.
All right.
There we go.
Yeah.
Sand touches. All right.
And then you need to go to the board. So we start at yeah.
What time is it? All right. So it's about 4:20 p.m. and we're doing 25 minutes.
Yeah.
So 4:20 to about 4:40. ch245. Yeah. Okay, cool. Alright, and it smells like vinegar, kind of, because that's probably the copper acetate with a little bit of...
Why does it smell like vinegar? It smells like vinegar, as Dr. Anderson is saying. It smells like vinegar because you have a solution of cupric acetate in acetic acid.
Oh, it's in the acetic acid?
Yeah.
Okay, so there's a lot of...
Yeah.
It's not just... I thought, yes, copper acetate, cupric acetate in acetic acid. That's why it smells like vinegar. All right, cool.
When they label the bottle, they did not label it right because it's copper sulfate in acetic acid.
Yeah, or cupric acetate in acetic acid.
Cupric acetate in acetic acid.
Yeah.
I will move a molecule. I will start with benzoin.
Benzoin.
Yeah. That's benzoin.
Benzoin goes secondary alcohol?
Yes. And you are doing just a partial oxidation of that. And here is the product. And that's benzene, the product.
So it goes from the alcohol to the ketone.
So, as you see, it's basically what is called a partial oxidation of benzoin.
Partial oxidation
of benzoin.
Yeah.
Because you have a secondary alcohol here. You know, when you oxidize a secondary alcohol, what you get it is a ketone. You go from here to here.
Cool.
That's a diketone.
A diketone, yeah.
So now, I will show you how to go from here to here. We have a couple steps. So, and I will draw this one like that. Okay.
There's 2 electrons there?
Yeah.
So okay, so it's a double bond. It's just, you're just showing the electron. There's 4 electrons total. 1 from the single bond, or 2 from the single bond.
Draw like that because I'm going to show the mechanism.
Okay.
So, first step. This one here. So, that goes to copper 1. I will do that close to it.
So it's losing losing electron, huh?
Yeah.
It's a electron transfer.
Yeah.
Which is kind of a weird thing, but yeah, that makes sense.
I'm making that simple.
Yeah. So there's two electrons in that double bond,
I drew that, yeah.
and one of them goes away. And you're left with
copper 2 plus.
Yeah.
To copper
1 plus.
Yeah. 1 plus.
And then you're left with that thing.
And you have a formation of what we call benzoin radical cation.
A radical cation.
Yeah.
Okay, cool. Okay. Radical, yeah, because you lost an electron, so now it's a cation.
Yeah.
And then you have the other top one is still a radical. So radical cation. Write that underneath. Radical cation. Radical cation. Okay, cool.
That's what you have. The next step. So I will draw the reaction here. You have
radical and the cation.
Here.
Yep.
And what happened? You know that you have cupric acetate.
Cupric acetate. Copper 2 acetate.
Yeah. Now that one is gone, what you have, you have that. ch234 minus.
Acetate anion, yeah.
Yeah. And as usual, one come and grab that. And this one goes here.
Okay. Oh yeah, towards the plus charge. Okay.
Yeah.
It's kind of like an elimination, like a E1 or something like that.
Yeah, kind of. And what you have here. Now you have that. So this one. See?
Yeah.
That's what we call that kind. It looks like an enol.
Enol, yeah.
It's a benzoyl enol radical, something like that.
So, okay,
but what is important is the enol here.
Yeah.
Plus acetic acid.
Acetic acid, because you just made acetic acid.
Yeah.
Here, when you had acetate, grab the proton. So now you have acetic acid right there. Okay.
We can call that enol, just enol. Yeah.
Okay.
That's an enol.
Enol, because it's kind of like it has an alkene.
Yeah.
En. All is the alcohol. So it's an enol.
Yeah.
They learn a lot about that in organic too, but for now, you know, you don't need to know too much about it. Just the basic structure of it. Yeah. All right. What do you do next?
Okay.
So you have the enol.
Okay. Erase top.
Yeah. Quite a mechanism, huh?
Eh?
Quite a mechanism.
Yeah.
So you got the enol, and there's a radical on the dot. O dot. Are you missing the radical?
Huh?
Are you missing the radical?
The radical has to be here.
Yeah.
See,
okay.
it's there.
So it's the enol, and then there's an oxygen radical.
Yeah. So.
Alright, so you're just recopying the enol.
Now, last time when you were doing the last experiment, remember you spoke about resonance. You have a resonance here. That.
Okay.
This one is that.
They're in resonance.
Yes.
Okay.
You wrote that R S and something last time.
Yeah.
Should I just write resonance?
Yeah. You're gonna write resonance? Is that what are you doing? You're right. Resonance. Yeah.
Are you already done with that in the lecture?
Yeah.
Okay.
Yeah. What's that? We're gonna do something kind of cool just to show how how they're in resonance. Because usually when we draw resonance, we draw these kind of curly arrows, sort of like a mechanism. But we can actually show how these are resonance structures. So I'm going to take the radical up here. So you can move it like right there, actually. All right, so we got the resonance, that radical. What we can do to show the resonance is kind of draw a fish hook.
Yeah.
A fish hook to show the radical go down.
Yeah.
And then this has a fish hook that kind of goes up.
Yes.
And that creates a double bond. That makes a ketone, which you see the ketone right there.
Yes.
Right?
Yeah.
And then we have another fish hook that goes there, which creates the radical. And then we see how that radical is formed. So that's a cool, anytime you have resonance, I always recommend drawing little radical arrows, resonance arrows. Yeah. And of course, this is the other arrow, which means resonance. Yeah. So it shows these things are in resonance. Yeah. So not in equilibrium. This is not the same as like a.
No, it's not that.
We don't want to do that because that's a different idea.
Yeah.
So by resonance, it means the electron is delocalized.
Yeah.
And both of these are correct representations of the same structure. Yeah. Okay, so that's a little bit on the resonance. Okay. Okay, go.
Now we move to the next step.
Next step.
So what will happen here, you still have C+ ion. It's better to draw that over here.
Okay. Our board is so small.
Yeah.
same as basically the second resonance structure.
Yeah.
Yeah. Yep.
And this one goes to the copper to plus that.
Yeah. So we often call that single electron transfer.
Yes.
It's basically the electron just gets kicked out.
Yes.
The electron goes away.
Yeah.
So it's the copper takes the electron away.
Yeah.
And you're left with a cation, I think, or
Well, with a cation, exactly.
carbocation, yeah.
So, I will draw the arrow
Yeah.
here. Huh?
Yeah. And so that the arrow is, you know, it's weird because we often draw those arrows like saying, oh, you know, it's like moving to make a bond. That's not what that arrow means.
Mm-hmm, no.
That in this case, the arrow means
Yeah.
the electron is being lost.
Yeah.
It's lost. We don't have a good arrow for that, so we just do that.
Yeah.
Sometimes though, well, I'll just say, this is my own comment.
Mm-hmm.
Sometimes I write SET. S-E-T.
Yeah. Which means
Single electron transfer.
Yeah.
And that gets the point across also that, you know, the radical is just going away. It's that electron is being moved from the organic molecule to the copper.
Copper to plus.
Yeah.
Which is reduce.
Which will reduce it. Yeah,
Yeah.
because it goes from copper 2 down to copper 1.
Yeah.
Yeah, that's cool.
Yeah.
There you go.
So now what you have here you have a push charge.
Yep.
Here you have a keto group. And here
Now you're almost done,
Yeah.
looks like.
and you have a
Copper 1.
copper one, which is basically reduced.
It says copper 1, and that's because you reduced copper 2 to copper 1.
Yeah.
Okay.
So now what is the next step?
You could just go like down and around.
Oh yeah.
Yeah. Yeah. Whatever you want. Whatever you want.
Because sometimes
Yeah.
depends.
So we're just gonna recopy.
Confused, yeah. I will just do that. Yeah. Next step.
Quite a mechanism, huh?
Yeah, it's a nice one too.
Yeah.
I will do that like that. This one here. And this one here. So now, you still have your push charge here. Here, you have your ketone. And now you have that.
Alright, which is the same as that structure.
The same as that.
After
Now,
Never mind.
what will happen now? You still have this one here.
Acetate.
Acetate. Okay. It will come and grab this proton here. So let me put this one
over there to the left.
It's better. It's better.
Yep, there you go.
And now I can do it like that.
You got 4 electrons on there. Okay.
So this one comes,
Yep.
like that. And this one goes here.
And that forms the double
And
bond.
then form
The product. That's pretty cool. And what's the name of the product again you make? It's called benzyl. It's a diketone. Cool. Quite a mechanism, but it's pretty neat.
That's also a review if you write for them.
Yeah. Yeah. You know, in the organic 1 class, they learn about some radical stuff and like radical halogenation.
Yeah.
They're only learning about oxidation coming soon in the lecture, but they use chromium, like chromium trioxide, stuff like that. So this is a different way to do the oxidation, and it's a specialized way, like for this molecule, but it's really cool. It's a really cool mechanism. So yeah, and it also has some resonance. It has the single electron transfer, just some kind of weird mechanistic steps. And anyway, yeah, it's you know, multi-step mechanism, and then you get out the ketone product. And OH there. Very cool. Very nice. And acetic acid. Alright.
So you want to add something?
What's that?
You want to add something?
No, nothing to add. I think you stepped through it pretty well. So very cool. Well, we have about 3 minutes. Let's check the time. Yeah, we're about 2 or 3 minutes. We're basically done.
Okay, so we'll come back to the board later.
Back to the board, okay.
You should be aware that it is also possible to synthesize this product, but this time by using nitric acid. Nitric acid.
Yeah. So you go from the alcohol and ketone to the diketone.
You use nitric acid as reagent.
Nitric acid. So nitric acid can be an oxidizing agent.
Yes.
So, because you are oxidizing, because you're going from 1 bond. You know, initially you had 1 bond to oxygen, alcohol. Yeah. Then you oxidize it. Then you get 2 bonds to oxygen.
Yeah.
And we call that an oxidation, oxidizing reaction.
Which is basically the oxidation of secondary alcohol, which gives
to the ketone.
Yeah.
Oxidation of a secondary alcohol to a ketone. Yeah. Cool. Alright, let's inspect this thing.
You have done a lot of radical chemistry in your PhD.
I did a lot of radical chemistry in my PhD. Different stuff. Look at that. It's pretty cool. It's sort of boiling and probably reacting. And in this condenser, we don't use water, right?
No water.
So it's because we're not too worried about there's that's acetic acid in there. We don't have to worry about it boiling away. So it just it'll climb up, and this is pretty cool still up here, and so it doesn't like escape. If this was really boiling and climbing up, then you'd flow some cold water in there and then up around. So anyway, that's pretty fun to look at.
You see, when you started, it was blue.
Oh, it was blue. I didn't realize that. Yeah. It went from blue to green, huh?
Green, yeah. Because at the last step, you have a formation of copper with oxidation number 1.
Oh yeah, that's interesting. Yeah, so it went from copper 2, which is blue, to copper 1, which is green.
Yeah, you have.
I did not realize that. Well, I knew the oxidation was happening.
You have that, which is also there. You have that.
Yeah, that's green.
Yeah, that's right.
Interesting.
With cool. Oxidation number 2, copper 2 plus.
Yeah.
Is blue.
Yeah.
And copper 1.
Yeah.
It's green.
Do you got the blue stuff again, just to look at it?
Blue stuff, yeah, we can show that then.
That's cool because you can follow the reaction by the change the color. That's very blue. Okay.
Yeah.
And if we were watching it during the course of it, you'd see it churn slowly from blue to green.
Yes, exactly.
Which we're on the board, so we didn't get to see it.
Yeah.
But yeah, it's very green now.
So first thing we do, we stop that, as usual.
Unplug the power.
Yeah. So now
it's still pretty hot.
Yeah. So bring that down like
drop
that.
It down.
I'm going to use that later.
Okay.
So and we're going to add 25 milliliters of ice cold water.
25. So you have some ice, and you're making add some water to it.
Yeah, add some
so
water.
It's cold.
I will better use that.
Okay, yeah, the beaker.
Yeah, the beaker is better.
Sure. Nice cold water.
And you add that from the top of the condenser.
Okay, slowly, probably.
Yeah.
Whoa, look at that.
Yeah.
Precipitation. So that's your product, I guess,
Yes,
right?
and you wait something like 2 minutes.
Wait 2 minutes. Yeah. That's cool. Look like.
Now we prepare for the next step.
And get ready for a vacuum filtration?
Oh yeah.
Okay, so we're getting ready for the vacuum filtration.
Yeah.
We have the flask ready.
Impression flask.
Yep.
The neoprene adapter,
Neoprene adapter.
Put that here. The Kirchner funnel.
Kirchner funnel.
The hose, we always have to check if the vacuum is working.
Use a yellow one for vacuum.
Yeah, the yellow one, that's the vacuum.
Yeah.
It's working very well.
Sounds good.
Yeah. Like that. What you do need now is a filter paper. I have some of them in my pockets.
Alright, so we have a paper.
So yeah, so I need to...
Yeah. On the board?
No, it's not here.
Oh, okay.
Just because I don't see
yeah.
I need to fix that.
Yeah. Alright, so we got the vacuum, or the vacuum hose going.
Yeah.
Now, does it look kind of crystalline-ish? It does look crystal. Let me see it.
Yeah, that's it.
It actually, yeah, it looks like something we can filter. A lot of white solid. That's what we want.
Yeah.
And the copper will stay dissolved, I think, and go through, right?
Yeah.
So you're agitating it a bit.
Yeah.
And then you're going to dump it in.
So you just need to add some water here.
So you're going to add a little bit of water. And then, shake it around and then dump it in again. So you washed out your flask a bit.
Yeah.
Cool. And so the product looks like that white solid. So that's the benzyl, the diketone?
That's the crude product.
Crude product,
because we're also going to recrystallize.
And you're going to recrystallize it?
Yeah.
And then maybe a little bit came through also, but we're probably going to throw that away.
But what you see at the bottom, that's
garbage.
the garbage.
Yeah, okay, but we have some apparent crude product, which is nice. Okay.
Yeah.
Okay.
So we bring that to balance.
You can get a crude mass.
Yeah.
looks like a nice material.
Yeah.
Well behaved, white solid. Scrape off the.
Yeah.
Get a nice good yield, hopefully.
Yeah.
Crude yield, because of the quite a lot of water in there still. Uh-oh, you a little bit came out on the balance. That's okay.
Yeah, that's fine. Okay, that's 0.94.
0.94
gram of crude product.
0.9495 roughly grams of crude product.
Yeah, what we have here is a crude product.
Crude product.
Yeah. And
a little bit
today,
on the balance. Do you want to get that out? Get that little. There's a little.
okay, good. Okay.
Get your yield up. There you go. Okay.
Yeah.
Alright, so we have our crude product, and you're gonna do now.
So what we have here is a crude product. We are going to purify that. So we started with it will be 0.94 gram of crude product before the purification. After the crystallization, we need to have an amount of pure product less than 0.94. That's very important to know.
Yeah, you shouldn't have the same amount or more.
Yeah. So the solvent you are going to use for the crystallization.
You're going to use some
95% ethanol.
Ethanol. That's a good recrystallization solvent.
Yeah.
Cool. So you're going to purify it by recrystallization.
Yeah.
And that's why you have the hot bath ready again.
Yeah.
Because you're going to heat it up.
Yeah. This time, no.
Don't touch it.
Yeah, don't touch it.
It's very hot.
You need a glass rod. And we need a 50-milliliter aluminum flask.
So that's where you're going to do the crystallization.
Yeah. So we need first the plastic funnel. You never go to a hot plate if you don't have all what you need inside the aluminum flask. But
okay, there's your material to purify.
Also in the aluminum flask.
It's pretty nice, white crystals. Okay, cool.
Yeah, but you cannot go to a hot plate now.
Yeah.
So I will get a small beaker.
So you're getting about 10 mils?
About 10 minutes of ethanol.
Cool. So it's
10 milliliters.
suspended in there. Yeah.
Now you can go to the hot plate.
You're gonna cook it up till it dissolves. So this is the recrystallization.
Yeah.
agitating it until it dissolves?
Yeah.
Has any of it dissolved yet, or no?
Some it has.
Okay, yeah.
It has to completely dissolve first.
Completely dissolved. It's getting there.
Yeah.
Are those the boiling stones from before? Yeah, I think so.
Yeah, I will take them.
Which is okay.
Yeah.
That's not going to hurt anything.
Yeah. Completely dissolved.
Completely dissolved.
So I need to let that
kind of
room temperature.
cool down and it might crystallize? Or?
Yeah. You know that crystallization is a slow and selective process.
Is it what?
Slow
Yeah.
and selective.
Selective.
And, you need to be patient.
Patience.
Yeah. And as usual, first thing we do, turn that off.
Turn off the heat.
Yeah.
Unplug
Unplug
it.
both.
Yeah.
And you wait.
And you wait.
Rolling stone out.
We're still waiting on this stuff to cool down a bit, and hopefully we'll get some crystals. You got a spatula?
Yeah, I got this spatula.
So you're trying to scrape it, or what are you doing now? You're getting rid of those things?
Yeah, rolling stone.
Get rid of the boiling stones?
Yeah.
Yeah. Because that may affect the crystallization if there's some weird stuff in there.
Yeah.
Okay.
So just wait.
Wait, there's one more, but that's...
Yeah. I will take that out.
Alright. Still waiting, and do we see anything? No. Don't see anything yet. Alright, so now you're putting it in ice, and that'll maybe accelerate crystal growth.
Yeah.
Cool. A little ice water, nice cold surface.
It starts to come slowly.
Let me see. What do we see here? Uh-oh, it looks like we have crystal. Is that crystals?
Yeah.
Oh yeah, we do.
Start to come.
Okay, so now let me see it real quick. I can't see it. Where is it? There it is. Yeah, we have the evidence of crystallized product. Good. Okay.
Yeah.
Now you can stick it back in there. Or?
Yeah. You see?
Yeah, I see it. Cool. Okay.
Put that
Back in the ice it goes. Yeah, I think taking the boiling stones out helps.
Yeah.
Because they're sort of crystalline themselves, and the crystallization gets confused if there's other solids.
You know, say whenever we have experiment in Ocam too.
Yeah.
Where we use charcoal. Charcoal.
Charcoal. Yeah.
You need to take them out.
Filter it out. Yeah.
Right.
So once you have a little bit of crystals, then you put it in ice, and then you'll get a whole bunch of crystals.
Yes.
It's seeded the process. Okay. Now it looks like you're just going to use the same one as before for waste, and then you'll just get a purified product on a new filter paper. Okay, so we're getting ready for another vacuum filtration of your purified product.
Yeah.
So we have a fresh paper.
Fresh paper.
Let's take a look at it again.
That's
tons of what appears to be tons of your purified recrystallized material. Okay, cool.
You know that the vacuum is working.
Vacuum's working. You have just a little bit in there,
little water.
You're just add a little bit of water. Is that what you're doing?
Yeah.
Ice water.
Some ice water, I think is better. Huh?
Yeah, because ethanol will dissolve.
Ethanol, yeah, will dissolve. Yeah.
Unless it's cold ethanol.
Yeah.
But yeah, this is fine. Let's take a look. that looks really good. Yeah, it's a lot. Also kind of a sugary white, crystalline solid.
Yeah.
Exciting. Alright. Then you let it dry for a bit?
Yeah, 1 minute.
About a minute or so, just let it dry under vacuum.
Yeah.
Alright, so we let it dry a bit. Turn off the vacuum, and then we go get a mass. Clean the balance.
Yeah.
Always got to be considerate for the next person.
Yeah. It's a 0, huh?
Not zeroed yet, it's still being funny.
I cannot see why.
Why is it being silly? Let's try power. There we go.
Okay, no, it's still lit. Yeah, let's wait.
I think it'll be fine.
Yeah.
Just give it a second. There we go.
Okay,
Zero.
no, it's a 0.
When all else fails, turn the power on.
Yeah.
Scraping it off there. It's cool. They're learning how to do some basic chemical reactions and synthesis. Organic 2 Lab is all about that.
Yeah.
But this is a good exposure to making new molecules, which is exactly what we did.
Yeah.
And isolating and purifying and everything like that.
So it's 0.3?
0.3, so it was what,
0.94?
Yeah.
Crude product?
0.94 and now it's 0.3, so lost about a third, or they got about a third out.
Yes.
30% yield or something from the purification step. 0.3 grams. 0.3 grams of purified product.
Yeah, which is correct.
Good. About
has to be less
normal.
than
yeah, if you have more, then you have a problem.
Yeah.
You can't create matter from no matter.
When you do the reaction, you also have formations. Of ammonium nitrate. It's even more dangerous stuff than ammonium nitrate.
Oh wait, nitrite.
Yeah.
You have nitrate and you form nitrite. Got it. That's ammonium nitrite.
Yeah.
What's ammonium nitrate?
Ammonium nitrate is this one here.
I know it's 3, right? Yeah. Cool. That's ammonium nitrate on the bottom.
Yeah.
Okay.
And this one, ammonium nitrate, ammonium nitrate.
Yeah.
This one here.
Yep.
And as you can see, the nitrogen here doesn't have the same oxidation number than the nitrogen over here.
Yeah.
So what happens during the reaction, because once it does come down, that has to be destroyed.
That's the what?
That has to be destroyed.
Destroyed. Yeah.
So, and what happened? We had here, good plus, okay. Yeah, we had that plus that went to 2 plus.
2 plus to 1 plus, right?
Yeah, I went first.
Yeah.
Like that.
Yeah.
But after that, this one here has to oxidize again.
Reoxidize.
Yeah, reoxidize.
Yeah.
That means that you have two plus, so it is two plus 1 electron.
Yes.
Balance.
It goes back from copper 1 plus back to 2 plus.
Yeah.
And then it emits an electron,
Yeah.
or it releases an electron. E minus?
No.
Is it an E minus?
Like that, huh?
Yeah.
That's how you
There you
wear
go.
that.
Yeah.
So now, what we do, I said, we have ammonium nitrate, which goes to that.
Yeah.
Okay. So I will write that again here. Now
Yeah.
I have which gives that. Now we need to balance that.
Yeah.
So you have one more oxygen here. And that here you are going to add some water. Okay.
Yep.
When you add water here, that means that you have 6 hydrogen in this side,
Yeah.
and you need 2 more here.
Yep.
Okay?
2H plus on the left. Yeah.
At the bottom, as you can see, at the bottom here, you have a 2 plus charge. That means that you need to add 2 electrons.
Yeah.
2. So, plus 2 electrons, and that is balance.
Aha. Okay.
So that,
Yeah.
yeah. See? That,
Yep.
that. Or it's better to put that in the same line, or it's okay like that.
That's probably fine. Yeah. That's
Okay.
okay. Yeah.
So, now, you know, in all redox process, you have 2 electrons here. You also need 2 over here.
Yep. Yep.
Okay? So that means that you need to
Put-
use all the top,
All of it in 2, right?
yeah, time 2. All
Yeah.
of that.
Yeah.
So that gives 2 plus gives 2, 0 2 plus. The electron can be gone.
Yep.
Because this was gone.
Yep.
So here can also be gone.
Yep.
Here you have at the bottom 2 is plus
Uh-huh.
plus
Yep.
gives
NO2.
plus H2O.
Now you have a balanced equation, huh?
No, I have balanced equation. So, but now, as I said, this one has to decompose.
Yes.
Okay, so and here something is missing. Here is 2 plus. Huh?
But you have those. It's already there.
Where?
Oh, you have it up.
No.
So it's really like
okay,
all,
yeah,
all
okay.
the left stuff and all the
Okay,
right
yeah.
stuff, right?
Okay, good.
Yeah.
So now you have that, but this one has to decompose.
Yes, that needs to be yeah.
Okay, and how it does decompose?
NH4, NO2, yeah.
Yeah, NH4.
So what you're saying is overall, you have the left stuff, all of the left stuff, and basically you can assume a single arrow to all the right stuff.
Yeah.
So all the left stuff, single arrow, all the right stuff.
Yeah.
And then you're going to talk about the decomposition of NH4,
I'm
NO2.
going to write all of that.
Yeah.
Later.
Yeah, probably good to rewrite it all.
Yeah. So you have 2 plus.
2 copper pluses.
Plus 2H plus.
2H plus.
Plus NH4. NO3.
NO3. Yep.
Okay, and then that
one big arrow.
Yeah.
Yeah, clean up and erase all this stuff.
No, which one?
All this stuff.
Okay.
Alright. So we have all the left stuff.
2 plus. Plus. Okay. Plus H2.
Yep.
So this one does decompose.
Yeah.
Okay. In N2.
Yep.
Plus 2H2.
Oh, okay.
This one decompose. I will say decompose.
Oh.
To that.
Okay. So that
now the final equation.
Let's show the whole equation.
Yeah.
Alright.
Is the following.
So that's kind of like the reoxidation of the copper is coupled to the reduction of ammonium nitrate to ammonium nitrite, and then ammonium nitrite is degraded to N2 and H2O. Cool.
Two plus NH, this one here,
yeah.
and 2 plus 3
H2Os total.
So you have 2
yeah.
here and 1 here. But that's
just to be clear, maybe draw a little. I don't know. It's a little.
Where here?
They can see it, I guess. So we'll step through it. Let's go from the beginning. So it looks like. So overall, now we just have the same thing basically. 2 coppers, 2 H pluses, ammonium nitrate. Then, if we consider the decomposition pathway of NH4NO2, it just makes 2 copper, 2 pluses, N2 and 3 H2Os, because you had 2 H2Os plus 1 H2O makes 3 H2Os. So that's cool. That's the overall process.
Remember one thing. So the stockroom did not really label that correctly, because there should be copper acetate, cupric acetate in acetic acid.
Sorry, let me see. Let me see but it says somewhere on the back. Flip it around. It does say cupric acid. It just does not say that it's acetic acid. So that's a little bit of a labeling error.
So now, what does decompose that? That's the acetic acid. You have the acidic medium here. You see here?
Yeah. So the decomposition is mediated or whatever by the acetic acid.
Acetic acid.
Okay, so that's in this step, the decomposition step. Well, it's caused by acetic acid.
Yes.
Without the acetic acid, it would not decompose.
You not decompose.
But overall, that's a pretty cool balanced equation that shows what's going on. So, and how, copper 2 goes to copper 1, which goes back to copper 2.
Yeah.
And the copper, and that's all mediated by the ammonium nitrate, which gets converted back to ammonium nitrite, which decomposes. Yeah. So yeah, that's a neat.
Don't forget that copper 2 is a part of a catalyst.
It's a yeah.
Cupric acetate, so
it's a catalyst. It is totally a catalyst because
it's go back to
it's regenerated.
It has to regenerate.
That's very cool. Okay. Okay.
So you see here a very easy way, which was written by Dr. Anderson. You start here. That's your starting material.
And pH, if you don't understand, is just a benzene. So
that's benzene.
That's an abbreviation for benzene.
I just mean phenol.
Yeah.
It's soluble. You go with that.
So
you have the benzene here, okay, which is soluble.
Yeah.
You put that in ice and water, and you have a product here which is not soluble.
And so the point that we're trying to make here is that there's something kind of cool about the acetic acid. It dissolves stuff. It dissolves stuff, and it also causes a lot of the reaction and the degradation of the ammonium nitrite and stuff. So it's involved in the reaction. It's also a good solvent. It just dissolves stuff, right? We saw it dissolve. So it dissolved this, and then we did the reaction, and the product was dissolved also, and then the copper changed to oxidation state. But then what you might be confused by is like why when we added ice water did it turn into a solid, right?
Yeah.
It was dissolved here, you added ice water, and now it was a solid. And the reason is because the water mixes with the acetic acid, the acetic acid, right?
Mm-hmm.
And it dissolves, and now like it just, you have an organic material that sees water and it doesn't know what to do, so that's why it turned into a solid. And that's just a really cool trick that we use often. Carry out a reaction in a solvent, add a water, and if the water dissolves in that same solvent, like water dissolves in acetic acid, then you get the product out. So just a really cool little trick that was done, and we just wanted to point that out. So anyway.